मेरा स्क्रीन शेयर हो गया?
Yes, sir.
Yes, sir. Yes, sir.
ओके, पेन ड्राइव नहीं लगा। ठीक है, स्लाइड विजिबल है?
Yes, sir.
हेलो
Yes, sir.
यार, ये भी कोई पुराना। ओके, so for coordinated complexes there are two types of geometries. You all know that one is square planar and other is tetrahedron. And square planar is an extreme case of distorted octahedron complex, and we'll talk about that in detail later on. That when an octahedron complex undergoes distortion, and that distortion extends to the extreme, two ligands depart finally at the transpositions, and then we are left with a square planar geometry, four coordinated geometry. So that distortion is known as tetragonal distortion. We'll talk about that later on. So tetrahedron coordination is closely related to cubic geometry. You know, cube is an geometrical entity which has 8 corners. How many square faces? 1, 2, 3, 4, 5, 6 square faces and 12 edges. That's what constitutes a cube. And imagine you have ligands at the corners of a cube, 8 corners of a cube, and send metal ion at the center of such a cube. And the axes or Cartesian coordinate axes, x, y, and z axes, pass through the center of the opposite faces, because there are 6 faces. Just हेलो, अभी मैं क्लास में हूं, बाद में बात करेंगे। So there are 8 ligands. Imagine a cubic situation. We have 8 ligands at the 8 corners of a cube, and x-axis passes through 2 opposite faces of the cube. Y-axis also passes through center of the 2 opposite faces, and z-axis also passes through center of the 2 opposite faces, because there are 6 faces in the cube, opposite faces. And the ligands are at the 8 corners, and you all know that there are 12 edges. So now just imagine the orientation of the d orbitals. How are d orbitals oriented with respect to the geometry of the cube? Dz square is aligned along the z-axis. That is clear. So it passes through the center of opposite 2 faces of the cube. And same can be said about the dx square minus y square, because this orbital also has lobes aligned along x-axis and y-axis. Therefore, this orbital also passes through center of the opposite faces of the cube. What about the dxy, dxz, and dyz, the set which we call T2G set in the octahedron geometry? What about their orientations? Where are they extending in this cubic geometry? We all know that they are in between axes, so they must be passing through center of opposite edges of the cube. So because there are 12 edges, each of them will pass through 4 edges. Why? Because dxy has 4 lobes. Similarly, dyz also has 4 lobes. So each of them is कोई बच्चा है, एक मिनट, somebody is joining. कौन है? आसिया मलिक. ठीक है। मेरी बात, मेरी आवाज आ रही है? मेरी आवाज आ
Yes,
रही है
Yes,
बच्चे?
sir.
ओके।
yes,
Yes,
sir.
sir.
तो मैं ये बता रहा था कि डी ऑर्बिटल्स, जो 5 डी ऑर्बिटल्स हैं, उनमें से 2 डी ऑर्बिटल्स जो डी जेड स्क्वायर और डी एक्स स्क्वायर माइनस वाई स्क्वायर है, वो 2 अपोजिट फेसेस, आप चाक का डब्बा समझ लीजिए, जो स्क्वायर, जिसमें स्क्वायर फेसेस होती हैं, क्यूब में हमेशा हर एक फेस स्क्वायर की होगी, तो वो सेंटर ऑफ अपोजिट फेसेस से गुजरेंगे। लेकिन जो दूसरे 3 ऑर्बिटल्स हैं, जिनको हम T2G ऑर्बिटल्स कहते थे, वो उनके लोब्स सेंटर ऑफ अपोजिट एजेस से गुजरेंगे, और हमारे लिगेंड जो है वो कॉर्नर्स पे हैं, न कि सेंटर ऑफ अपोजिट एजेस पे हैं। इसलिए पहली बात ये समझने की है कि हम इस ज्योमेट्री में लिगेंड्स जो है वो डायरेक्ट कन्फ्रंटेशन, डायरेक्ट मतलब कोइंसिडेंट, ये अपना एक लाइन में नहीं है ऑर्बिटल्स के साथ, जो कि उसमें था अपना ऑक्टाहेड्रन ज्योमेट्री में। लिगेंड्स डायरेक्ट इसी लाइन से आ रहे थे जिस लाइन पे डी ऑर्बिटल्स अलाइंड थे, मतलब वो एक्स एक्सिस पे था लिगेंड, और डी एक्स स्क्वायर माइनस वाई स्क्वायर भी एक्स एक्सिस पे था, डीजेड स्क्वायर जेड एक्सिस पे है, और लिगेंड भी जेड एक्सिस पे डायरेक्ट आ रहा था। तो 1:1 डायरेक्ट कन्फ्रंटेशन में था लिगेंड और डी ऑर्बिटल। वो सिचुएशन यहाँ पे नहीं है। यहाँ पे लिगेंड है, मैंने तो बोला 8 कॉर्नर्स हैं और हर एक पे लिगेंड है, लेकिन एक्चुअली हम इसको टेट्राहेड्रॉन जनरेट करने के लिए ऑल्टरनेट कॉर्नर्स पे लिगेंड हटा देंगे, एक पे रखेंगे एक पे नहीं रखेंगे, तो आपके पास 4 लिगेंड्स आएंगे। 4 लिगेंड आएंगे, इन एनी केस दे आर एट द कॉर्नर्स ऑफ द क्यूब। 4 लिगेंड्स हैं, क्यूब के कॉर्नर्स पे हैं, लेकिन जो डी ऑर्बिटल है अपना T2G सेट जो है, वो सेंटर ऑफ अपोजिट एजेस से गुजर रहे हैं, न कि कॉर्नर से गुजर रहे हैं। इसलिए डायरेक्ट एक लाइन में लिगेंड और ऑर्बिटल्स नहीं है। तो इसका कॉन्सिक्वेंस क्या होगा कि आपके ये जो लिगेंड है, ये डी ऑर्बिटल्स हैं, वो जो रिपल्शन फेस कर रहे थे ऑक्टाहेड्रॉन ज्योमेट्री में, यहाँ पे पहली बात तो है कि रिवर्स होगा, डीजेड स्क्वायर माइनस वाई, डीजेड स्क्वायर और डी एक्स स्क्वायर माइनस वाई स्क्वायर, वो तो बिल्कुल वो दूर हैं अपने लिगेंड से, क्योंकि लिगेंड कॉर्नर पे है और वो सेंटर ऑफ अपोजिट फेस से गुजर रहे हैं, इसलिए उनकी रिपल्शन बहुत कम होगी, वो बिल्कुल रिपल नहीं होंगे। रिपेल होना था अपना T2G सेट ने, जो नजदीक थे, वो एज के सेंटर से गुजर रहे हैं, लेकिन वो कॉर्नर से नहीं गुजर रहे हैं, इसलिए उनकी रिपल्शन थोड़ी ज्यादा होगी दूसरे सेट से, लेकिन इतनी ज्यादा भी नहीं होगी। तो पहली बात हमने ये समझनी है कि टेट्राहेड्रॉन ज्योमेट्री में स्प्लिटिंग जो है डी ऑर्बिटल्स का बहुत कम होगा। क्यों कम होगा? क्योंकि जो ऑर्बिटल डिस्टेबलाइज होना था वो dxy था, dxz था और dyz था। वो इन लाइन, एक लाइन में, जिसको ज्योमेट्री में बोलते हैं क्विंसिडेंट, अगर 3 पॉइंट्स एक लाइन पे हों तो उनको बोलते हैं क्विंसिडेंट। तो वो ये क्विंसिडेंट नहीं है, जिस डायरेक्शन में लिगेंड है उसी डायरेक्शन में ऑर्बिटल नहीं है डायरेक्टेड, थोड़ा सा उससे दूरी पे है, वो सेंटर ऑफ एजेस से गुजर रहा है ऑर्बिटल, और लिगेंड जो है कॉर्नर पे है। तो उस वजह से रिपल्शन इतनी डिस्टेबलाइजेशन नहीं होगी, तो स्टेबलाइजेशन भी उतनी ज्यादा नहीं होगी। विद द रिजल्ट, द एनर्जी डिफरेंस बिटवीन T2G एंड EG is less as compared to what was happening in the octahedron geometry। एक वजह ये है, और दूसरी वजह कम स्प्लिटिंग होने की ये भी है कि यहाँ पे लिगेंड्स कम है, वहां पे 6 लिगेंड्स थे और यहाँ पे 4 ही लिगेंड्स हैं, राइट। तो टेट्राहेड्रन कोऑर्डिनेशन is related to cubic coordination. Consider 8 ligands aligned on the corners of a cube with metal at the center of the cube. Axes X, Y, Z pass through center of opposite faces, and ligands are at the corners of the cube. So dx square minus y square and dz square are directed to the center of opposite faces of the cube, and dxy, dxz, and dyz are directed towards center of edges of the cube. So dx square minus y square and dz square are away from the ligand and face less repulsion, whereas dxy, dxz are more close to the ligand and face more repulsion, right? What is the so opposite? So they face more repulsion. Now remove the ligands, alternate ligands from the alternate corners of the cube. It results in a tetrahedron geometry. Now ligands are not directly confronting any d orbital in the tetrahedron geometry. because ligands are at the corners of the cube and dxy, dxz and dyz are directed towards center of opposite edges. Now, if they are not in one line, अगर एक लाइन में होते तो एंगल जो है 180 डिग्री का होता है. अभी वो एक लाइन में नहीं है, ये मेटल है, मेटल के इधर है अपना ये d ऑर्बिटल और लिगेंड यहाँ पे. तो व्हाट इज द एंगल बिटवीन देम? the angle between ligand metal and dxy orbital, or for that matter dxz बोलिए, dyz बोलिए, it is 1/3 of the tetrahedron angle, the angle that is between the two ligands. So that is 35 degrees 16 minutes. And in the case of T2G or EG orbitals, the angle is 109 divided by 2, that is 54. So angular distance के हिसाब से T2G orbitals are more close to the ligand, whereas EG orbitals are away from the ligand. So T2G orbitals will face more repulsion or will be destabilized, whereas EG orbitals will are stabilized, and the extent of stabilization and destabilization will be such that overall the barycenter, the center of gravity of the stability will be maintained. This is the geometry. ये अपना क्यूब है जिसके alternate corners पे ligand है और बाकी हटा दिए गए. और look at the orientation of the d orbitals, right? So मेरे पास है, this is the dx square minus y square, right? And this is dz square orbital. And look at the dxy, they are passing through the edges or not to the corners of the cube, right? So what is the consequence? Tetrahedral field, the dx square, this is barycenter, isolated iron atom, then raised to some energy, then dx square minus y square and dz square, they are stabilized, and other three are destabilized. But the extent of this delta t, the magnitude of the crystal field splitting, is less than what was found in the octahedron geometry. And it is 4/9 times what is found in the identical situation in the octahedron geometry. Now, T2 orbital. Now, the symbols used here are T2 and E, because center of symmetry is not present in the tetrahedron. Therefore, symbol G is omitted. We write T2G in the octahedron. Here in the tetrahedron, we write only T2. T2 orbitals are repelled more than E set. Crystal field splitting much weaker for tetrahedron complexes as compared to the octahedron complexes. Value of the crystal field splitting is 4/9 times this. Why this 4/9? Where from it comes? It has two reasons. Number one, number of ligands is 2 less in the tetrahedron than in the octahedron. If you compare the ligands, there are 6:4. The ratio is 6:4, and 6:4 का या 4:6 का जो simple ratio है 2:3 है. That's why tetrahedron delta will be 2/3 of the octahedron. Right side पे octahedron होना चाहिए था, गलत लिखा है मैंने. So एक तो ये वजह है 2/3 का. The direction of approach of the ligand does not coincide with the direction of the d orbital. This reduces the ligand further by 2/3. Therefore, this 2/3 and that 2/3 becomes 4/9 delta 0. So that's the reason why the tetrahedron crystal field splitting is 4/9 times the octahedron splitting, right? Now, the example is two metal complexes with identical ligand, identical oxidation state, identical metal, identical oxidation state, but one in the hexa coordinate, other is the tetra coordinate, one tetrahedron and one the octahedron. Look at this splitting. This is in centimeter inverse. 10,200 in the case of octahedron, only around 6,000 for the tetrahedron. So the pattern of splitting is reverse now. E orbital is down and T2 is up, and the amount of energy the T2 up is plus 0.4, and the stabilization for the E is minus 0.46. So delta T never is small because of the reason just we stated. It is never large enough to form a low spin complexes. So all tetrahedron complexes are high spin complexes. You will never find high spin, low spin options in the tetrahedron complexes. Nearly all tetrahedron complexes are these high spin. And secondly, because the center of symmetry is not there, they are colored. If you have identical, say for example, the complex which is listed here, cobalt hexamine and cobalt tetramine, both of the compounds are having same metal ion, same oxidation state, same ligand. Only difference is one is hexa coordinate, other is tetra coordinate. The tetra coordinate complex, tetrahedron complex, second one will be intensely colored, whereas the first complex will not have such a deep color. The reason is that when you have, we will talk about that later on, but you just remember right now that tetrahedron complexes in general are intensely colored as compared to their octahedron counterparts, because when the center of symmetry is lost, the transition, DD transition, becomes more intense. The molar extension coefficient improves, the probability of the transition increases, or the chances of the electronic transition increases. It becomes more allowed, and the octahedron complexes, the transition is forbidden, and it is allowed for in the case of tetrahedron complexes. Therefore, one identification, crude identification of a tetrahedron complex is that they are intensely colored when you compare their color intensity with the octahedron complex. And in terms of the scientific parameter which is used to identify the intensity of the color is molar extension coefficient. Molar extension coefficient will be in 1000 in the case of tetrahedron complexes, whereas in the octahedron complex it will be in the 100. So that's the parameter which is used to measure whether a particular transition is allowed or not, or if it is allowed, to what extent it is allowed. If the molar extension coefficient has high value, that means transition is allowed. So delta T is never large enough to form a low spin complex. So all tetrahedron complexes are high spin complexes, intensely colored. When the ligand field becomes extremely strong and the coordination has to be 4, then it is square planar complex. Tetrahedron complexes are not formed in that situation, right? So what is the crystal field stabilization energy in the case of tetrahedron complexes? It is now reverse of what we have been writing for the octahedron complex. Minus 0.6 times x is the number of electrons in the Eg orbitals now, plus 0.4 y, and y is the number of electrons in T2g orbitals into delta T plus NP, the pairing, how many electrons. These are the values that have been calculated for the tetrahedron complexes. For D1, the crystal field stabilization energy is minus 0.6 delta T, and the configuration is Eg1. So for T2, it is minus 0.12. For D3, it decreases because next electron has to go into the higher energy orbital. And D4, it still decreases. D5, as usual, has zero crystal field stabilization energy. This is true for the octahedron as well as tetrahedron complexes. Then you go to D6, it starts increasing again. D7 increase 1.2, and D8 0.8, and D9 again decreasing trend. D10 is 0. So if you remember yesterday's lecture, the highest values for crystal field stabilization energy for high spin complexes was D2 and D8, right? And in the case of octahedron, and that value was minus 1.2. And in the case of not D2 and D8, it was D3 and D8. Was it D8? Yeah, D2 and D3 and D8. Vanadium 2 plus and nickel 2 plus. These were the two situations, D3 and D8, which represented highest crystal field stabilization energy in high spin complexes. And look at the situation in the tetrahedron. It is D2 and D7. It is D2 and D7 which have highest value of the crystal field stabilization energy. Right? This is the same thing. So this is comparison with the octahedron. Huge splitting in the case of octahedron, small splitting in the case of tetrahedron. So tetrahedron 4 by 9 octahedron. And, and also the sequence of orbitals is reversed. T2G orbitals stabilized in the octahedron environment, T2G orbitals destabilized in the tetrahedron environment. This is how crystal field stabilization energy changes with the number of electrons, with the configuration, DN configuration of, this is for high spin complexes in both situations, tetrahedron as well as octahedron. Tetrahedron तो है ही नहीं low spin, octahedron की बात कर रहा हूँ. So blue line is for tetrahedron. So blue curve is much lower than the other curve, because the crystal field stabilization energy is much small in the case of tetrahedron complexes than in the octahedron complexes. And also the peak here is for D2 for tetrahedron, whereas peak for the octahedron is at D3. Another peak for tetrahedron is at D7. Peak for the octahedron is at D2, D8. So it is D3 and D8 in the case of octahedron. It is D2 and D7 in the case of tetrahedron, where the crystal field stabilization energy has the peak, and then it declines again. Now let's go to the other geometry, that is the square planar geometry. As I said earlier, it's a case of tetragonal distortion. Square planars are derived from the octahedron geometry. Two transligands in ML6 compress or elongate. That is known as tetragonal distortion. So you have Z compression. Z is taken as the arbitrary direction, but it can happen in the X direction. It can also happen in the Y direction. Remember, in an octahedron, there are two ligands along the X-axis, plus X and minus X, two along the Y-axis, plus Y and minus Y, two along Z-axis. So 6 ligands along 3 mutually perpendicular orthogonal Cartesian coordinate axes, right? And if you have any two ligands, trans ligands in any direction, either getting longer or getting shorter, that is what we call tetragonal distortion, right? And elongation is what happens during this square planar complex formation. So why does this elongation or compression happen? Number one, the reason is that you may have different types of ligands linked to the same metal atom in a complex. So we call such complexes mixed ligand complexes. There are two kinds of ligands in a complex, that is AB4, MA4B2, MA4. There are 4 ligands of one kind, and there are 2 ligands of another kind. And suppose the ligand along the 2 ligands B2s, Bs, there are 2 kinds of ligands, A and B. The ligand A is a stronger ligand, and ligand B is a weaker ligand. So there is a lot of repulsion along the X-axis and Y-axis. There is less repulsion along the Z-axis. With the result, the repulsion is less, or the bond weaker along the Z-axis, and therefore it is longer, and it is stronger in the X and Y-axis, and therefore XY bonds are shorter. That's the one reason why this distortion should happen in a complex. That the origin of this distortion, the reason of this distortion, is that you have 2 kinds of ligands linked with the central metal ion. The second reason is that sometimes electronic configuration is so inherently unstable that all the ligands are identical. We don't have different ligands, and therefore the origin of the distortion is not, the reason of the distortion is not lying with the ligands. It is lying with the electronic configuration of the metal ion, and that is known as John-Tauler distortion. We'll talk about that in this semester or probably next semester, the origin of charge transfer, John-Tauler distortion and its consequences, right? But at the moment, it is enough for you to say that sometimes some configurations, electronic configurations, are inherently unstable, that they lead to distortion, or this what we call the tetragonal distortion. So as I said earlier, there are two kinds of distortions. Sometimes it can be happen reverse way. That is, you have a mixed ligand complex A bond is longer because A is a weaker ligand. So in that situation, we will have Z compression, the first one, Z compression. If it is reversing, that is the ligand is stronger and B is weaker, obviously then this Z elongation will take place, that the bond along Z direction will be longer and weaker, and bond along X and Y direction will be shorter and stronger, right? So the distortion is not favorable situation because it leads to loss of the bonding energy, because whenever a bond becomes longer, other bond becomes shorter, there is loss of energy, bonding energy. But in some situation, distortion is inevitable. You cannot escape distortion when the situation becomes out of control, because there are differences in the ligands. Ligands exert different, repulsion in different directions. Obviously, then there will be distortion. You can't avoid it. So Z elongation means when the ligand along Z direction is weaker, it causes less repulsion to the d orbitals, and therefore the bond formed along the Z direction is weaker and longer, whereas the bond formed along X and Y axis, Y directions, are stronger and shorter, right? So in terms of the crystal field theory, I must say that in an octahedron environment, when the ligand along the Z direction is weaker, then it will cause less repulsion to those orbitals which are aligned along Z direction. And we all know that there are three orbitals which are aligned or completely aligned or near the Z axis. One of the orbitals is dz square, which is perfectly aligned along the Z axis. So this orbital will be strongly affected by this changing scenario, that this will feel now less repulsion, or in other words, this orbital will be stabilized rather than getting destabilized. It will get now stabilized. Why? Because ligand along this Z direction is now a weaker ligand. It is exerting less repulsion, and therefore dz square orbital will be stabilized to some extent. And the other orbital is dx square minus y square in the EG set. That is aligned along X and Y direction, and ligand along the XY direction is stronger ligand, therefore it feels more repulsion. So what is the consequence? That the EG set, which had two orbitals, dz square and dx square minus y square, that set will undergo splitting. It will split. Dz square will be stabilized, and dx square minus y square orbital will be destabilized, right? So in the same fashion, when you look at the T2G set, it has three orbitals. Two of them have Z in their names, dxz and dyz, and one of the orbital has dxy. So they will also feel different repulsion. dxz and dyz, which share Z orbital, they will have Z direction, will have less repulsion, and they will be stabilized, and dxy will be proportionately destabilized. So this scenario will result in splitting of the T2G set as well as splitting of the EG set, right? So now non-Z orbitals, they are, what are the non-Z orbits? Those which do not have anything to do with the Z direction. They are dx square minus y square and dxy orbitals. They are less repelled, and they are more repelled and destabilized, and EG orbital splits, dz square is stabilized, that and dx square minus y square is destabilized. Now, I have not written this. Yes. When this splitting happens, the names change. The origin of these names is group theory. We will talk about that in the next semester. I can't tell you the logic or rationale of these symbols, why we are using T2G and EG. But at the moment, T stands for triplet. There were three orbitals, therefore it was named T2G. Or G stands for center of gravity. center of symmetry, and E stands for doublet, right? And the doublet also undergoes splitting. Then the symbols A and B are used. So dz square orbital is given symbol A1g. Square is given as symbol B1g, and the lower orbital T2g split is written as EG, and dxy is written as B1g, B2g. So that's written here. The EG splits into dz square. It is written as A1g, and dx square minus y square. It is written as B1g. T2g splits into doublet. These orbitals are stabilized because z direction feels less repulsion, so they are written as EG, and dxy feels more repulsion. It's called uh, B2g. So delta E, the energy difference between B2g and B1g, these two orbitals which are repelled, both of them are repelled. Remember, when it was octahedron situation, the energy difference between T2g and EG was called crystal field splitting. Now, both these orbitals have been raised in energy, right? By same amount. So the energy difference between them will be called crystal field splitting, right? These complexes are formed, square planar complexes are formed by D8 metal ions with D8 configuration in presence of strong field ligands, right? This is the diagram which will make it more clear. This is T2g, this is octahedron, T2g and EG, right? And this is distortion. It is still octahedron, when the two ligands along the trans direction are weak and four ligands along the x-axis and y-axis are strong. What is the consequence? That the orbitals along the z direction will feel less repulsion, they will be stabilized, and orbitals along x and y direction will be destabilized. So this set splits into two. This is called A1g and this is called B1g. And this set also splits into two subsets. Dxy orbital is raised in energy because it feels more repulsion. Dxn and dyz feel same repulsion, and therefore they are still degenerate. This is Eg, dxy and dxz and yz is called Eg, and this is B2g. This is still 6 coordinate complex in which four ligands are shorter, bonds with the four ligands are shorter, and ml bonds with the two ligands, trans ligands, is longer. Now increase the length of those trans bonds and then ultimately remove them, you are left with square planar, you are left with 4 coordinated complex. That is represented by this portion of the diagram. This is the distorted octahedron, and this is extreme distortion when the two trans ligands have been completely removed. That's what I said in the beginning. Square planar is a special case of the extreme distortion of the octahedron complex, tetragonal distortion. So what is the consequence when you remove the ligand altogether along the z direction? Dz square orbital is more stabilized. It becomes lower in energy than even dxy. Dxy orbital is raised in energy. And dx square minus y square is raised in energy. So energy difference between dxy and dx square, this is known as crystal field stabilization energy. This is E, the order of the energy levels is Eg, then A1g, then B2g, and B1g. So if you have to add the, suppose you have a nickel complex forming nickel hexacyano complex, forming forming an square planar complex. So 8 electrons are to be accommodated. 4 of them will go here, 2 of them will go here, so that is 6, and next 2 will go here, that is 8, and this orbital will remain empty because this is huge, delta is huge as compared to the pairing energy. That happens in the case of square planar geometry. Remember, in the case of nickel, if you have nickel tetrachloro complex, that is tetrahedron. This is high spin complex. The moment you add cyanide to the nickel, it forms square planar complex. It does not form tetrahedron complexes because tetrahedron cannot have a low spin complex, so it forms an diamagnetic complex, and that is electrons are here, them two here and two here. So this orbital means, so low spin complexes. This is the configuration: E4, A1G2, B2G2, and B1G0. Right. So EG4, A1G2, and B2G2. हाँ बताओ, नहीं कोई काम है, यहाँ पे रख दो या किस बाकी से भरा दो, फिर बाकी ने भर दिया, भरा दे बाकी से यार, से जो बेले बैठे हैं। अच्छा ठीक है, हायर इज द एनर्जी इज dx, जितना फील्ड ज्यादा स्ट्रांग होगा, दिस ऑर्बिटल विल बी destabilized, right? And there that will this orbital will be stabilized by the same amount, so that will make the complex more stable. ये वाला orbital और stable हो जाएगा dz square, or these orbitals, these two orbitals will be more stabilized, this will be destabilized. And lower orbitals will be stabilized by the same proportion. Examples of the complexes are nickel tetracyano, nickel platinum, ये सब D8 हैं, platinum 2+, palladium 2+, platinum 2+ again, and gold 3+, that is D8. अच्छा, एक बात यहाँ पे समझने वाली है, निकल अगर क्लोराइड के साथ कॉम्प्लेक्स बनाए तो वो टेट्राहेड्रॉन होगा, लेकिन प्लेटिनम और प्लेडियम क्लोराइड के साथ भी स्क्वायर प्लेनरी बनाते हैं, वो टेट्राहेड्रॉन कभी नहीं बनाते हैं। उसकी वजह यह है कि एज वी गो डाउन द ग्रुप, द क्रिस्टल फील्ड स्प्लिटिंग जो है वो सिर्फ लिगेंड पे ही डिपेंडेंट नहीं है, लिगेंड कोई जिम्मेवारी नहीं है कि क्रिस्टल फील्ड जनरेट करना, इट डिपेंड्स ऑन द नेचर ऑफ द मेटल आयन आल्सो। एज वी गो डाउन द ग्रुप, इफ यू टेक सेम लिगेंड और एक किसी ग्रुप में, जैसे क्लोरो कॉम्प्लेक्स बनाइए किसी ग्रुप में, किसी क्रोमियम में, मॉलिब्डेनम में और टंगस्टन में, ये तीन ये मेटल्स हैं, एक ही ग्रुप में है ऊपर से नीचे की तरफ, तो सेम मेटल हो, मतलब सेम ग्रुप के हो, सेम ऑक्सीडेशन स्टेट में हो, और सेम ज्योमेट्री के कॉम्प्लेक्स बनाइए, मान लीजिए ऑक्टाहेड्रन बना दीजिए आप तीनों के, और लिगेंड सेम हो, तो क्रिस्टल फील्ड स्प्लिटिंग जो है वो नीचे की तरफ जाते हुए बढ़ती है, ऑलमोस्ट 50%, 3D से 4D में जाए तो 50% इंक्रीज होता है, 4D से 5D में जाए तो 25% और इंक्रीज होता है, कि मेटल की नेचर पे भी डिपेंड कर, क्योंकि डी ऑर्बिटल जब बड़ा हो जाता है, 4D का साइज बड़ा है 3D से, और 5D का 4D से भी बड़ा है, तो जितना डी ऑर्बिटल डिफ्यूज्ड होता है, बड़ा साइज का होता है, उतना उसकी रिपल्शन लिगेंड के साथ क्रिस्टल फील्ड स्प्लिटिंग में ज्यादा हो जाती है, और आपका क्रिस्टल फील्ड स्प्लिटिंग बढ़ जाती है। तो इसीलिए प्लैटिनम जो है क्लोराइड के साथ भी स्क्वायर प्लेनरी बनाएगा, कभी टेट्राहेड्रॉन नहीं बनाएगा, लेकिन निकल के साथ ऐसा नहीं है, निकल के साथ जब क्लोराइड के कॉम्प्लेक्स बनाते हैं तो दैट इज टेट्राहेड्रॉन, वेयर साइनाइड के साथ उसका ऑक्टाहेड्रॉन, ये अपना स्क्वायर प्लेनर कॉम्प्लेक्स बन जाता है। सो that is all about the square planar geometry and its splitting. Now, what are the factors which affect the magnitude of the delta? Number one factor is oxidation state of the metal ion. So, generally it is observed that crystal field splitting increases with increase in the ionic charge on the central metal ion, because the basic premise of the crystal field theory is that the metals behave as point charges, and there is electrostatic attraction and repulsion between ligand and metal. Metal is positively charged, that's why it draws ligands towards itself, right? And in the process of attracting ligands towards itself, d orbitals feel the repulsion. The brunt of that attraction is felt by the d orbitals, and they undergo splitting. So obviously, if the charge on the metal ion is high, positive charge, the ligands will come more close, and consequently the splitting of the d orbitals will be more, and therefore delta will have higher value. So ruthenium complex, same metal, same oxidation state in both complexes, same ligand, but oxidation state different. Same metal, same ligand, same geometry, but oxidation state changing here. +2 and +3. Delta is for +2 it is around 20,000, and for +3 it is more than 28,000. So huge increase. अच्छा, एक मिनट ना, नेक्स्ट क्लास किसका है? 1 बजे क्लास तो नहीं था किसी का? थोड़ा और बोल दूं? हेलो मुसरत,
Yes, sir.
हेलो,
Yes, sir. Yes, sir. Anna
हेलो,
ma'am की class है।
हाँ, वो ले रही है क्लास?
सर अभी तो मैसेज नहीं आया सर, शायद ले लेंगी, वो थोड़ा लेट लेती हैं।
उसने लिंक वगैरह भेज को? हेलो,
हाँ जी
हेलो,
सर।
यार बात नहीं कर रहा, उन्होंने लिंक वगैरह भेजा?
सर अभी तो लिंक वगैरह नहीं भेजा सर, तो 10 पे भेज देते हैं वो सर।
10 मतलब?
सर 110, 2 से 3 मिनट्स हैं
ओके,
अभी सर।
अच्छा, तो अगर उन्होंने भेजा तो अदरवाइज मैं थोड़ा कंटिन्यू करूं?
ओके सर।
अगर जो ही वो बोलेंगी ना तो मैं मुझे बोल देना आप, ठीक है?
ठीक है सर।
इज दैट ओके?
ओके सर, ओके।
कंटिन्यू करूं? इन केस वो नहीं आती है तो मैं थोड़ा कंटिन्यू करूं। अगर जो ही वो आपको मैसेज करेगी ना तो मुझे आप बोल देना, मैं लॉग आउट कर लूंगा, ठीक है?
ठीक है सर। ओके सर।
ओके, शुड आई कंटिन्यू? ओके, so one factor is obviously the charge on the metal ion. So larger the charge, larger should be the as per the premise of the crystal field theory, that the delta should increase, and it does increase in most of the cases. So then second is nature of metal ions. As I said, when you go from 3D to 4D, and then again increases when we go from 4D to 5D. So say for example, when you prepare a complex of chromium and molybdenum with same oxidation state, same geometry, and same ligand, the delta increases by 50% in the case of what is the value in the say it is 20,000 for the chromium. For the molybdenum it will be 30,000. So because 50% of the 20,000 centimeter inverse is 10, so it becomes 30,000. That's huge increase when you go from 3D to 4D. So similarly, complex of cobalt and rhodium, they are also in the same group, and there also the delta increases by 50%. But when you go from 4D to 5D, the increase is not by same proportion. It is increases there, but not by say 50%. It is 25%, and we all know that the reason is lengthenide contraction, right? The d orbitals become somewhat they shrink, and the repulsion is not so high. Then 4D and 5D always form because of this reason, that 4D and 5D metals never ever form high spin complexes. They always give them a weak ligand, even then they will form the low spin complex, because the magnitude of the delta is determined not only by the ligand but also by the nature of the metal ion. Therefore 4D and 5D metal ions rarely form high spin complex. They always form low spin complexes, right? Then the third point is that number and geometry of the complex, that we have the geometry of the ligands should have been number of ligands and the geometry of the complex. So if you have 4 ligands, this we have already discussed. If you have 4 ligands, that they will generate less crystal field splitting, and 6 ligands will generate more. So that's what we have already discussed in the case of tetrahedron octahedron situation. Now last thing and most important is the nature of ligand, right? So this is the high point of crystal field theory, that it could rationalize to some extent, and it also led, this factor also led to the downfall of the crystal field theory. Crystal field theory lost its relevance by this factor, that If you have a complex CR6 complex, what they did that they prepared a series of complexes of chromium with chromium 3 plus with a series of ligands having same geometry, octahedron geometry, same oxidation state, same metal, but ligands were different, and then recorded their absorption spectrum. And absorption spectrum, has three features. One is how many bands are there, at how many positions the absorption is happening, how many lambda maxes it has, how many, or in other words, how many transitions are possible in that complex. That was same in all the complexes, because the number of transition is dictated by the number of energy levels, and that is same because metal is same, oxidation states are same also, etc. So the geometry was also same, so the number of bands was same in all the cases. However, the position of bands and the intensity of bands, that was varying from complex to complex. And what was monitored was what is the position of bands, right? How does it change position of the band, lambda max position of the band? Sometimes it was 28,000, in the next complex it was 27,000 centimeters. So position of band was monitored by while the ligand was changed. So the new one, the new one is written as the lambda max of the first band. The first band, we'll talk about this new one, etc. in the next semester, probably. Yes, next semester, not in this semester, when you discuss the electronic spectra of the transition metal complexes. So the first transition gave the value of the delta, the 10 decays. So there was steady increase in delta, in the value of the lambda max, when you change the ligating atom from fluoride to oxygen to the nitrogen, right? So ligand, oxygen is also weak, nitrogen is best base and it is better ligand, and therefore we were expecting this trend, and that was observed, that the position of the band increases with the basicity of the ligand, or etc., or the dipole moment of the ligand, right? And the effectiveness with which the ligand was forming the bond. And in terms of the crystal field theory, it was said that those ligands which create more repulsion with the d orbitals, they were responsible for increase in the lambda max, increase in the frequency. So a series of ligands were used, and the lambda max, or the new one, was made, and on that basis, on the basis of the data that was accumulated in the process, the ligands were arranged in a series, and that series is called spectrochemical series. So spectrochemical means that this series is developed from the spectroscopy, from the electronic spectrum of the complexes. So this is the experimental series. This is not the theoretical series based on some theoretical model. It was the experimental data, and on the basis of that experimental data, this is the series that ligands were arranged in this order, that the ligands like cyanide and carbon monoxide are the generating the highest splitting, whereas ligands like iodide, bromide, sulfide, they are the weakest, right? And this series, whereas crystal field theory could account for some some trends, but this series led to downfall of the crystal field. For example, why should water have uh, uh, you know water is a stronger ligand than OH negative, whereas the basic premise of the crystal field theory was that there is repulsion between the positively charged metal and the negatively charged ligand, or if the ligand is not negative charged, then the dipole of the ligand. So ligands and metal were believed to be acting as point charges. So a negatively anionic ligand should cause more repulsion than a neutral ligand. So this is not happening. Water is stronger ligand, causing more repulsion than OH negative. So obviously there is something wrong with either with this experimental data or with the basic premise, basic principle of the theory. So secondly, these are the values before going into the failure. These are the values for your reference. This is the return. This is in your Hui's book. The data there. So vanadium complex, vanadium in the +4 oxidation state, and see the one is tetrahedron, one is octahedron, and see the delta in centimeter. This huge difference. Same metal, same oxidation state, but geometry different. Octahedron complex. Similarly, there are other complexes, or you can see for yourself. This is the data again for different metal ions where the ligands have been changed. See in the cobalt, water, cobalt amine, cobalt ethylene diamine. So oxidation state same. Oh my God. Oxidation state, all octahedron. Look at the, the delta. When you change the ligand, it is with water, it is 20,000, with ammonia, 22,000, with ethylene diamine, chelation happening, 23,000. Similarly, when the cobalt is in the +2 oxidation state, right? Change of, you can compare this one with the +3 oxidation state. This is just 9,000, and ammonia 10,000, and then tetraamine, tetrahedron, only 5,900. So this is data for your reference, right? This is the experimental data spectrum. Also in the Hui's book, I've taken this diagram. You can see it. This is not visible clear there. You can see it from the book more clearly. The position of band was monitored. See, the position of band is at lower wavelength. It is now increasing, now going more towards the right direction. And on the basis of this, spectrochemical series was developed. Spectrochemical series could rationalize the spectra, and you could predict what could happen with the different ligands. But serious difficulty in the interpretation of the crystal field theory. What was the serious difficulty? That on the basis of the principle of the crystal field theory, anionic ligands were supposed to be more stronger ligand than the neutral ligands, but it's not happening as per the experimental data. OH negative is a weaker ligand than water, and similarly, ammonia is the dipole moment than ammonia. Water should have been this stronger ligand than the ammonia, but experimentally it is reverse. And when you have cyanide ligand, delta increases very by a small margin when you go from 3D to the 4D or to the 5D metal ions. So these difficulties, these shortcomings led to the downfall of crystal field theory, and the better thing is that it also led to the development of the alternative theory, that is ligand field theory, and then ultimately to the molecular orbital theory, which we will discuss next time, right? So questioned very foundation of the crystal field theory, and eventually it led to the development of ligand field theory and then to the molecular orbital theory. That's all. थोड़ा और था, वो कहाँ गया? चलो, we'll do next time. थोड़ा और रह गया है, that we'll do tomorrow. अगर अभी मैडम का नहीं आया लिंक तो we can discuss some questions. आवाज नहीं आ रही है? हेलो?
यस सर, बीच में बड़ी बात कट रही है.
ओके, चलो अब तो मैंने खत्म भी कर दिया यार. सॉरी, मेरा कंप्यूटर खराब हो गया कुछ, तो नेक्स्ट टाइम मैं प्रॉपरली इंतजाम करूंगा. तो किसी को अगर कोई डाउट है तो पूछ लीजिए प्लीज. अभी मेरी आवाज आ रही है? हेलो?